Thanks for being here. I will talk about testing of large-scale distributed systems. Before I start, a little bit about myself. I started my career as a web developer, then switched to automation and performance testing. I used to work for companies with a completely different profile, built social networks, computer games, instant messengers, CDN solutions, and so on. And for the last 5 years, I've been involved in banking software, working for the largest bank in Central and Eastern Europe. I'm not sure if I can name it because just recently I left my job there to join another company, Dell Technologies. And what I'm going to talk about. First, about fault injection, the method I use to test large-scale distributed systems. What it is, how I came to it. And then about an object of testing, the new IT platform, the project where I took part in. And there will be some stories and demos. You also will know about tools and frameworks which I use. All the examples you can download from my GitHub. And as a database, I will use Apache Ignite. But all these approaches can be easily applied to any other modern database. OK, let's start. The first story. This happened when I worked at Rambler. Rambler is an internet company, Russian internet pioneer. The company where Nginx web server was created. Back in 2005, we just launched a new web service for our users, a social network. Everything was good, but in a while we realized that the number of our users had grown so much that capacity of our simple two-tier architecture, a database application servers, had become insufficient. Our social network wasn't able to cope with the growing load. We started thinking how to fix the situation, and finally we had a look at Memcached. Then this technology was used in a popular website for bloggers live journal, if you remember. Basically, Memcached is a hash table in RAM with access to stored object by key. When you need some object, say user profile, the application first goes to Memcached, and if it's not there, it goes to the database, creates an object, and puts it into Memcached. So next time, when you need that object, it will be fetched directly from Memcached. Due to the use of data caching in RAM, we had significantly relieved our database, and our social network was finally able to cope with load. But it was too early to celebrate, because along with the increase in performance, we got new problems. Let's talk about this. When you need to change data, say user profile, the application first goes to database, and makes some changes there, creates a new object. And this new object should replace the old object which was in the Memcached. And at this particular moment, a failure happens. Application itself got hung up, or network connection disappeared, or Memcached server failed. For some reason, we couldn't update the old object with the new one. And we have two different profiles, one in the database, another in Memcached. Our users log into the social network and see the old profile data and don't understand what's happening here. Would it be possible to find this bug with functional testing or with load testing? I don't think so. Honestly, most likely we would have missed it. But all these types of testing are simply not intended for this. But there is a type of testing which is specifically created to catch such bugs. I think you have already guessed. It's called fault injection. This method deliberately introduces faults into the system and ensure it can withstand with error conditions. Next story. This graph shows statistics which I took from the Bank of Russia on transactions carried out with payment cards issued by Russian banks. You can see in 2017, more than 17 billion transactions were made to pay for goods and services. Next year, in 2018, more than 24 billion transactions were made, with an increase nearly 7 billion transactions a year. Incredible, isn't it? According to our estimates, the bank will process more than 10,000 transactions per second in 2 years, and it's quite a lot for banking transactions. By that time, we have to complete our digital transformation. And therefore, several years ago, the bank began to build so-called new IT platform, which will satisfy the growing needs of its customers and will allow them to offer new services. New IT platform should be easily scaled horizontally, and by scaling horizontally, I mean not only storage space, but also computing resources. And the new IT platform should be based on open source software. Expensive mainframes from large vendors should be replaced with affordable low-end hardware. And the platform should guarantee reliable operation. All the hard data should be stored in RAM. Thank God it's not that expensive now. The new IT platform is based on Apache Ignite. More precisely, we use GridGain, paid plugin. The technology has fairly rich functionality. It combines properties of relational database, NoSQL database. It can be used as a data storage platform, or it can be used as a computing platform. This technology is relatively new, and therefore, the bank performs acceptance testing for each GridGain release on its own infrastructure before pushing it live. While designing the new IT platform, we came to the conclusion that system components can and will fail. Say you have a cluster of 200 low-end servers, then you will have hardware failure at least once a month. And this situation we will consider is completely normal. This situation should be handled correctly, and our users should not notice them. But it's not just enough. It's not enough to design the system stability to test the system stability. It's necessary to test that the system can withstand with error conditions. As Katie McCaffrey from Microsoft Research said, there is no other way to check that your system will behave correctly in case of possible failure without explicitly forcing it to fail. And the more complex and distributed your system, the more cases you have to check. Next story. Let's have a look at an example, a banking application that simulates fund transfers between bank accounts. The application transfers $50 from account A to account B. And this process might be shown like this. The application consists of two parts: an Apache Ignite server, data storage, and Apache Ignite client. We have a cache which stores 10 bank accounts. Basically, the key is in account ID, and the object is in account, the value is an account object. In total, 10 such objects will be created. Accordingly, we will have the total balance will be equal $1,000. And let's see how it works. It's the method to create accounts, and then we Yes, we got the expected value. The total balance is equal $1,000. Let's make our application a little bit more complicated. Let's make it multitasking. In reality, with the same bank accounts, can work with many. With the same bank accounts, can work many client applications. So we can see the total balance is $1,364. The client rejoices. The bank suffers losses here. And let's see why the parallel launch of two tasks led to this result. In this slide, you can see how two tasks simultaneously change the state of account A. And since the second update overrides the first update is lost. This problem is called the lost update anomaly. And obviously, with this code, we will not get correct results. In order to make our application work as it should, it's necessary that our database supports ACID transactions, and our application takes this into account. The ACID abbreviation is especially essential when it comes to banking software. And I think many here know what it is, but in order to understand why this is so important, let's take a look at as it applies to our banking application. So atomicity means that transaction is atomic and indivisible. Either all the proposed changes are reflected in the database, or none of them reflected in the database. Say there is a transaction that transfers money from account A to account B in several steps. And after step 3, the transaction fails. In this case, the changes made by this transaction prior to this step should not go to the database. Consistency means that transaction takes the database from one consistent state to another consistent state. For our remittance example, this means that the sum A plus B should not be changed after transaction has committed. And the total amount of money, the total balance should remain constant as well. Isolation. The effects of a transaction may not be visible to other transactions until the transaction has committed. Say there is in our transaction that reads state of account A and account B after step 3 and before step 6. For this transaction, the amount A plus B is less than it should be, and the total amount of money is less as well. Durability. After the transaction has committed, its changes permanent. Client received notification about transaction, money was transferred from one account to another. The changes permanent. The ANSI SQL standard defines 4 levels of transaction isolation for different possible outcomes for the same transaction with different possible outcomes with the same transaction scenario. And I find it really interesting that the standard doesn't impose any specific locking scheme or mandate particular behavior, rather describes all these isolation levels in terms of these 3 phenomena. that are rather permitted or not at a given isolation level. Many modern databases like Oracle, Postgres, Microsoft SQL use read committed as a default isolation level, and for nodes for this particular isolation level, we'll have the same result as we didn't use transactions at all. Apache Ignite supports 2 concurrency modes and 3 isolation levels. And you can use it with various combinations which may result in different answers. And for our particular example, we can choose between pessimistic repeatable read or optimistic serializable. And the difference between concurrency mode when the lock is acquired during prepare step of two-phase commit protocol in optimistic transactions, and in pessimistic transactions during first read or write access. And let's see how it works. TXStart method takes 2 parameters, enum parameters, concurrency mode, which is optimistic, and isolation level, serializable. We will transfer money within transactions. Well done. Well done. We got expected the total balance. Congratulations. Now next story. Let's test under load. There is plenty of tools for performance and load testing. I prepared my examples with GMeter. GMeter is free software and solves our task 100%. Let's have a look at how it works. We will make our application multi-node. I will add 2 extra nodes. Now we have 3 server nodes. The cluster is running. Now create a cache. The total balance is equal to $1,000. And there is a SQL line utility which allow me to execute SQL query against the cluster. We got expected total balance, a total $1,000. And now we can specify the number of parallel users. It will be 3, which will make transfers between bank accounts. Then I wouldn't like to rewrite already written code in Java, so I will use JSR223 plugin, which allows me to write script directly in Java. I will compile jar archive from the classes of my application and upload it to the test plan. Now let's write the script and run it. You can see how users are transferring money between bank accounts. And then we'll suddenly stop one of the nodes and check the total balance for all the accounts. Wow, 692. The bank's brand and its reputation is completely damaged. The clients are in panic. So what did we do wrong? Actually, we didn't choose the right cache mode. And Apache Ignite supports three cache modes: local, which is not listed here, and partitioned and replicated cache mode. We can choose between two of them. For our case, ideal solution will be partition mode because it's suitable for large data sets when updates are frequent. We have one instance of data within the cluster, or we'll have one instance plus several backups within the cluster. And I set up 2 backups and run our application again. Suddenly stop one of the nodes and check the total balance. Well done. We managed to make our application work correctly. And now make our tests even more complicated. Let's test under load, and during this load, let's introduce faults into the system. In this case, I will use Jepsen. Jepsen is a framework for distributed systems verification. Basically, it's a Clojure library. Clojure is a modern Lisp functional language. And here you can see the typical Jepsen test settings. It consists of some settings of distributed systems, about distributed systems, and what kind of concurrency we need. And also there is Nemesis. Nemesis is a special process which introduces faults into the system. You can emulate network segmentations, you can kill nodes, you can resume nodes, you can pause nodes, you can change system times, and even you can create your own Nemesis. And let's see how it works in practice. Jepsen setups distributed system, waiting for the cluster is started. Then run a bunch of operation against that system. You see how the money is transferred between accounts. And after that, we analyze that the history of those operations makes sense. And it makes sense, looks good. Everything worked correctly. Well done. Next story. 2 years ago, before we starting the new IT platform, we went to our operations engineers and asked them, guys, what can break in our system? What should we test? The answer was, everything can break. You have to test everything. Of course, we were not satisfied with this answer, so we sat together and analyzed all the statistics for the previous years and found out that the most probable case which we might encounter would be not failure. Moreover, this can happen for absolutely different reasons. For example, an application may fail, or JVM may crash, or operating system may crash, or even worse, hardware may fail. All the possible cases we divided into 4 groups. wrote tests for them and called them disruptive scenarios. So we have hardware, network, application, and other scenarios. Hardware. For each partition in the cluster, there are 1 primary node and 3 backup nodes. So we have 4 copies for each partition. And each copy is stored on a different server. And this means if the server fails, it will not be a big problem for us. It will not be a big problem for us since we have 3 copies of 4. And even the whole data center fails. It's not a big problem for us either, since in each data center we have 2 copies of 4. We emulate scenarios related to network segmentation with IP tables utility. NetM utility is used to emulate various network problems. And another interesting case we test is split brain. Split brain is when all the cluster nodes are alive, but due to network segmentation, they can't communicate with each other. Actually, it's a medical term, which means the brain is divided into 2 hemispheres, each of which considers itself the only one. And the same can happen with the real cluster. Connection may disappear between 2 data centers. For example, 2 years ago, due to the damage of optic fiber cable by an excavator, clients of Russian bank, Rocket Bank, could not perform operations over the internet for several hours. ATM didn't accept credit cards, terminals didn't work. And in our case, this situation should be handled correctly. Since most of the software we use is written in Java, we use test cases related to the Java world. We are subject to all the problems related to the Java world. And we test Apache Ignite, the cluster, with various garbage collector settings. And also we test cluster with the nodes that have off-heap overflow. Off-heap is a memory area managed by Apache Ignite itself. It's much larger than Java heap. And of course, we test the whole system. We test it on different levels. What happens if we shut down one of the nodes, or what happens if we increase the response time for one of the microservices? Other cases, other scenarios. Other scenarios include cases related to data recovery utilities. So these utilities allow us to recover in case of major accidents. In this slide, you can see tools which we use to test. And personally, I would recommend you to use Jepsen. It's completely free software, and we even wrote Jepsen Test for Apache Ignite. And I think now every mature database, open source database, has Jepsen Test. And lessons learned. What I would like you to remember from my talk. First of all, fault injection. The method which deliberately introduces faults into a system to ensure it can recover from error condition and can withstand it. What have we learned from using fault injection? You can't test everything. When choosing a test scenario, you have to proceed from your business risks. For example, in financial area where I used to work, it's important to check integrity, consistency of data. It's important to make sure that data is not lost anywhere in case of failure. You have to write tests the way that test results are clear and unambiguous. Your test environment should be as like production as possible, and also it's an important point that your data should mirror production data in volume and data types. And you have to test under load. Testing only in one single user mode, you will not find, probably will not find many bugs. Personally, I don't know which technology I will use in a year or two, but I'm pretty sure I will use fault injection. The method really works. It helps to find a lot of bugs, and it's suitable for any technology, and it can make your application more reliable, much better. That's it. Questions, please? Actually, it's off heap size. Off heap is a memory area that's managed by Apache Ignite itself, and it allows to process petabytes of data. And it depends on you, but we used to work with nodes which have 668 gigabytes of heap. It depends on your task. I can tell you how we run that test. You specify your business scenario, and then you introduce faults into your system. Then you check the history of those operations that was run against the system, and you have to make sure that the history of those operations makes sense. It might be like, in my example, it was a total balance, and for your example, it might be something different. It's not real data, but we use special tools to obfuscate data to make it to remove all the private information from there. And yeah. It makes a difference, actually, yes. You have to, your test data should mirror production data in volume in data types. It's from our experience. Yeah. We use, actually there was no details, but it was, we have some special utilities which allow us to recover to a specific point in time, like there's a utility which is called Peter, in which you can recover to a specific point in time. And this allows us to run tests against fresh system. Yeah, that's how it works. We have tests tests that last 1 day, and there's actually some different levels of testing. I have some basic acceptance testings, and there is some. After that, we run more specific testing, like concurrency, isolation levels, and because for us it's important to give response immediately as fast as possible. So we use different levels of testing, and usually the whole test suite lasts like 1 day.
Are you involved in the actual design of the system that you create? Do you use something like TLA plus?
Yeah, that's really interesting. Yeah, we are thinking about TLA plus using, but it's currently we use Jepsen. But next step will be TLA plus. Yeah, because yeah, it's really interesting case. Yeah. Good point. Actually, I was tried to make it really straightforward. I would like to give you something like you can use. In our company, we use HP Performance Center, which is a really good tool. It supports more than 50 protocols, and we can use it for the whole team. Like. I know Gmeters has some features, but for me it's not my case because we use HP Performance Center. But yeah. Load runner? Nah, what is this?
It's the custom tool.
Actually, a load runner is HP Performance Center is based on load runner. Yeah, it's HP Performance Center is a web interface, and it's used for big teams like we have. And load runner, it's for like small teams when you don't need to communicate with each other. Because with HP Performance Center, I can see who is running tests now and how many tests we have run, and stuff like that. So all the statistics and so on.
Within virtualization tools, you have three architectural functions from another tool. Which one do you prefer?
Actually, yes, there were two tools, and they for different cases. Yeah. IP tables for network segmentation, and in our one, Netom is for emulating network problems. You can.
When you say network segmentation, just cutting off the entire. If I understand it correctly.
Yeah, we can create random segmentation, actually.
Have you used it directly or some wrapper through Java?
We use it directly. Yeah.
It would have been so useful if there was wrapper for the GridGain.
But you can use Jepsen, which can emulate. How it works. We started creating our own scenarios. Then we had a look at Jepsen, and now we really satisfied with this tool, and we would like to continue. We can because we can change it. It's open source, and it really works. It's good.
I found out about Jepsen Test yesterday. It's great results, but I mean, different people here.
At TLA Plus is really good as well. We will look into it.
I can see them being a great couple of years.
Yeah. So. I think time's up. Thank you.